During this lesson, you will use compasses and iron filings to map a magnetic field around a bar magnet. You will draw magnetic field lines to represent magnetic fields. You will compare and contrast magnetic fields around different types and combinations of magnets, showing how the fields interact. Finally, you will explain the phenomenon known as aurora borealis in terms of the Earth's magnetic field and sonic wind.
Hello again. At the end of our last program, before I got attached to this magnet, I asked you how this cow magnet got its name. Did you find out what, if anything, it has to do with a cow? Those of you who live in rural areas probably already knew. But did you city kids find out? Well, a cow magnet is actually fed to a cow in order to attract and hold pieces of iron objects that the cow may pick up while grazing. If the sharp objects were allowed to go through the digestive system or be regurgitated when the cow chews its cud, severe damage could occur. So the magnet keeps the objects in the cow's stomach. If and when the cow is slaughtered, the magnets are retrieved and recycled. Ew. That's probably more information than you wanted to hear, huh? Now that we've cleared up that question, let's get right to today's topic, magnetic fields. When we studied electrostatics, you learned to draw lines of force to represent electric fields. We can do the same to represent a magnetic field. So while I get down from here, you need some guidelines.
To represent a magnetic field lines are drawn. The direction of a magnetic field is defined as the direction the north pole of a compass needle would point in the field. Magnetic field lines outside a magnet are always drawn from north to south.
Since the direction of a magnetic field line is the direction a north pole would move in a magnetic field, we can use a compass needle to help us map the field around a bar magnet. If you have small compasses and bar magnets in your school, your teacher may want you to do this lab with us. If not, watch as our students do the work.
We'll start close to the north pole of the magnet and make dots on the paper to mark the position of the north and south poles of the compass needle. Naturally, the north pole of the needle points away from the north pole of the bar magnet. Next, we'll move the compass a little farther from the magnet so that the south pole of the needle lines up with the last dot made. We'll make another mark where the north pole points. As we continue this procedure, notice how the compass needle's position is changing in response to the magnetic field around the large magnet. Finally, our marks return to the magnet at its south pole. We'll start the next field line closer to the middle of the magnet. When we've mapped out the field line, we can see that the line doesn't extend as far out from the magnet as the one originating closer to the pole.
If we repeated this process closer to the middle of the magnet, the field lines would look like this. And if we did the same thing on the other side of the magnet, the lines would be identical. At the poles of the magnet, the field lines would look like this, with the arrows pointing away from the north and toward the south poles. Inside the magnet, the field lines would form closed loops like this. However, you won't need to draw these, since we'll be concentrating on the field around the magnet.
Mapping magnetic fields using the compass method would take a long, long time. But there's an easier way. Remember in the last program how we used iron filings in a test tube to represent domains in a nail? Well, we can use them in a different way to map a magnetic field. Each little piece of iron, if it is free to move around, will act like an individual compass needle. The only problem is that no north or south pole is marked. So you'll have to add your own arrows from north toward south. Again, your teacher may want you to do this lab along with our students. Stop the tape now and get everything ready for the lab. Or, if you're just going to watch the lab, get a copy of the lab sheet so you'll be ready to draw the magnetic fields as you see them. Local teachers, give your students the lab report sheet from Program 10-1 from the Facilitator's Guide. In this part of the lab, we'll use iron filings to map the same magnetic field around a bar magnet. Each small filing will act as a temporary magnet and line up with the magnetic field. A bar magnet is placed in the holder, and a sheet of paper is put on top. Iron filings are sprinkled on top of the paper, evenly all around the magnet. The paper is tapped to help the filings line up with the magnetic field. Notice where the field lines are most concentrated. On your lab sheet, draw 10 to 12 field lines to represent the field around the magnet. Don't forget to use arrows to show the direction of the field lines, away from north and toward south.
Here is another view of the field around a strong bar magnet suspended between two sheets of plexiglass. The filings on top of the magnet are responding to the field above the magnet. Although we commonly represent magnetic fields as being flat, the field actually surrounds the magnet in 3 dimensions.
If you sprinkle the iron filings evenly all around the magnet, and then tap to help the filings align with the field, you'll see that the filings are more concentrated around the poles. What does that tell us? Well, watch this demonstration. I'll place this paperclip on the north pole of a magnet and let it go. You can see that it doesn't fall, defying gravity. The same thing happens at the south pole. Now watch what happens when I release the paperclip under the middle of the magnet. Evidently, the magnetic field is strongest at the poles and weak in the middle.
When we draw magnetic field lines to represent a magnetic field, the closer together they are, the stronger the field. The number of lines in any given region is called magnetic flux. Magnetic flux is greatest around the poles of a bar magnet. This strong magnet is made of a rare ferromagnetic element, neodymium. The magnetic flux is so great that the magnet can attract the ink on the dollar bill, which contains small amounts of iron compounds.
Now you should be able to answer this question. What is the advantage of using a horseshoe magnet instead of a bar magnet? Tell your teacher. If magnetic fields are strongest around the poles, the advantage of a horseshoe magnet is that the poles are close together. So you can use both poles at once to double the pickup force of the magnet. Let's go back to the lab and see the magnetic field around a horseshoe magnet and the interaction between the magnetic fields of 2 magnets. In each case, we will give you time to draw about 8 field lines to represent the magnetic field. Don't forget to use arrows. If you need more time to draw what you see, ask your teacher to pause the tape or rewind it so that you can see it again.
This time, a horseshoe magnet is placed in the holder. Iron filings are used as before to map the magnetic field. On your lab sheet, draw 6 to 8 field lines to represent the field, concentrating on the area around and between the poles. Next, we'll line up 2 bar magnets with the north pole of one facing the south pole of the other, about 5 centimeters apart. We'll sprinkle the iron filings between the magnets and around them, and we'll tap the paper as before. On your lab sheet, draw 6 to 8 field lines to represent the field, concentrating on the area between the magnets. Finally, we'll line up 2 bar magnets with the north pole of one facing the north pole of the other, about 5 centimeters apart. We'll sprinkle the iron filings between and around the magnets and tap the paper as before. On your lab sheet, draw 6 to 8 field lines to represent the field, concentrating on the area between the magnets.
Here's what the magnetic field around the poles of a horseshoe magnet looks like. The magnetic flux is greatest between the 2 poles. Next, you saw the magnetic field between the north pole of one bar magnet and the south of the other. The lines are drawn from north to south poles, with the flux being greatest between the 2 magnets. And last, you saw the field around the north poles of 2 magnets. The fields repel each other, with the lines bending away from each other like this. The magnetic flux between the 2 magnets will be very small. Now, you draw the field between 2 south poles. You should have drawn the same shaped magnetic fields as in this case, only the directions are different with the arrows pointing toward the south poles.
Here's a challenge for you. Under this paper, I've placed a magnet, a wood block, and a stack of soft iron washers. I've also sprinkled iron filings on top of the paper. Now, I'll tap the paper to help them line up with the magnetic field. Can you tell me where the 3 objects are? Tell your teacher. Well, it's easy to locate the magnet, isn't it? And did you say that the washers are here because the magnetic field is distorted in this area? You're right. But where is the wood block? It's impossible to tell. That's because certain substances don't affect a magnetic field. Let's go into the lab and compare different materials and how they affect a magnetic field. Then we'll talk about some practical applications.
This apparatus tests for the ability of a material to affect a magnetic field. A magnet is suspended close to the opposite pole of another magnet. The attraction keeps the suspended magnet in place. When one index card is moved through the space between the magnets, nothing happens. But let's try 5 index cards, filling more space. Nothing happens. The paper has the same effect as air. Now we'll try a razor blade. The suspended magnet wiggles, so we know that the razor blade has affected the magnetic field. Next, we'll run a stream of water between the magnets. No effect. When we move a straight pen between the magnets, we see that the pen has more effect than air. Is it the metal that affects the magnetic field? Let's try another metal, aluminum foil. Again, no effect. So only some metals affect a magnetic field. Which metals do you suspect? Tell your teacher.
Did you conclude that only ferromagnetic metals can affect a magnetic field? You're right. Materials like my finger paper, wood, and cotton all have the same effect as air. You can shield electrical forces by placing insulators around charged objects, but you can't insulate against magnetic forces. So hiding a gun inside a suitcase, surrounded by towels and cotton underwear, won't keep it from being detected in a metal detector. How do metal detectors, like the ones in airports, work? They contain a magnetic field that is produced by current flowing through coils of wire around the opening. There's a link between electricity and magnetism, and we'll discuss that in our next program. When a ferromagnetic substance goes through the detector, it alters the magnetic field, which can then be detected by the electronics in the device. We'll learn more about that in our next lesson too.
Here's a physics challenge for you. Some traffic lights are designed to turn green only when a car approaches the intersection. How does the traffic signal know that your car is there?
You should have used what you learned about metal detectors to answer the challenge question, because they operate on the same principle. This time, the coils of current-carrying wire are buried in the street. When the steel body of the car passes over the coils, the magnetic field is altered, and a signal is sent to the traffic light to turn green. Once again, physics explains so many things in the world around us, but can it explain the magnetic world itself? Namely, the planet Earth and the magnetic field that surrounds it. Where does the Earth's magnetic field come from anyway?
We know that a magnetic field surrounds the Earth and that it's shaped like the one that would surround a strong bar magnet placed at the Earth's center, like this. But to answer the question, where does the Earth's magnetic field come from, we're not sure. We know that there is not a magnetized hunk of iron at the center of the Earth because it's far too hot for domains to remain aligned, so that's out. Another idea involves the molten or liquid part of the Earth's core. Some scientists believe that there are currents in this region that surrounds the solid center, and the slow movement of charged particles would create a magnetic field. There are other theories, but whatever the cause, we know that the Earth's magnetic field is not stable. In fact, we know that it has changed poles at least 170 times, with the most recent reversal occurring about 700,000 years ago.
Now, how do we know that the Earth's poles have flip-flopped that many times? Well, Earth scientists have studied rocks that have formed from molten iron-containing materials. It seems that the iron atoms in the molten material tend to line up with the Earth's magnetic field. So when the iron solidifies, a record is left of the direction of the field. As they date and analyze different layers formed throughout geologic time, we get a record of the Earth's changing magnetic field. There is no regular pattern, so we can't predict when the next reversal will occur. So don't throw away your compasses just yet. And don't touch that dial, because I want to show you some beautiful pictures of a phenomenon that is related to the Earth's magnetic field. It's called the Aurora Borealis, or Northern Lights. Enjoy the photographs now. We'll explain later. You can imagine all the myths associated with these strange and beautiful lights. If you lived in Alaska or other northern places, you could see them often. But even if you can't see the northern lights, you can still see the light about what really causes them. As I tell you the story of these lights, fill in the blanks in your notes. It all starts out on the sun. Now, the surface of the sun is very hot.
How hot is it?
It's so hot that solids, liquids, and gases don't exist. It's so hot that electrons jump right out of gaseous atoms, producing the fourth phase of matter, plasma. Plasma consists of charged particles, and these particles rush out from the sun and through the solar system as solar wind. When solar wind reaches the region of the Earth's outer atmosphere called the magnetosphere, their motion is controlled by the Earth's magnetic field. Because moving charged particles are surrounded by their own magnetic fields, they are repelled by the Earth's magnetic field here. So most of the people on Earth never see an aurora. But the charged particles can slip through the Earth's magnetic field at the poles and enter the atmosphere. In the atmosphere, the charged particles collide with electrons in atoms of oxygen, nitrogen, and other gases, and transfer energy, making electrons jump to higher energy levels. If you remember your chemistry, you know that when the electrons fall back down, they give off different colors of visible light. The aurora borealis is the result of billions of electrons jumping and falling at the same time. The colors depend on the type of gases in the atmosphere.
Here's another physics challenge for you. Another aurora appears in regions close to the South Pole. What is the other name given to these southern lights? See if you can find this information and tell your teacher.
You may have thought magnetism was just something to play with. Now you know it is all around us and affecting us all the time. Magnetoman will be back in a minute to share even more magnetism trivia with you. But first, it's time to show what you know.